Hi, everybody. Can you hear me okay? Yeah, great. So before we start with our speaker, I wanted to ask professors if they had any announcements they wanted to make. Anybody? Going once, going twice. All right. Oh, Professor Bear. Oh, yeah. So today, the seniors handed in their final research papers after working on their research project for a whole year, and they got to ring the bell in Dirigo, so maybe we should give them a round of applause. It's a huge accomplishment. Anything else I'm forgetting? Thursday, yes, thank you. Thank you. Thursday, they will be presenting the results of their projects at 12:30 in Alumni Hall in Levitt. So if you have some time in your schedule, we'll go all the way till 3 o'clock. So you should come and see what they've been up to. You can see nice charts and figures and maps and stuff that help explain their results. So you'll hear from me again about that. All right, then I want to introduce our speaker. We have Chris Horvat, who's going to be talking to us about changes in sea ice on the poles and how they're related to what's happening there. Chris is a senior lecturer at Auckland University in New Zealand and assistant research professor at Brown University, where he oversees the antipodal oceanography group. Together, they work to understand how polar, marine, ecological, and human systems interact, particularly in the present period of rapid Arctic change. Chris has a PhD in applied mathematics and a master's in the same field both from Harvard. And he has a bachelor's in math and physics from the University of Pittsburgh. He's also the subject of a documentary called Beneath the Polar Sun, which he's going to talk about in a little bit. So I will hand the screen over to Chris now.
Cool. Yep. Thanks very much. And it's really nice to be speaking to everyone, although I can't see anyone. I trust you're there. And yeah, so my name's Chris Horvat. Thank you for that introduction. And I'll talk a bit about, what makes polar regions so interesting throughout the course of this talk. There's 3 links here. I can come back to them later if you like, if you're more curious about the work that we're doing as a part of this broad climate initiative called SACIP. So that's bottom left. I have a personal website, which is the green box, and then my group has its own website, which is on the bottom right, which is changing from the Brown Polar Oceanography Group to the Antipodal Oceanography Group once I move to Auckland. So a couple things that we'll discuss we'll mostly talk about polar oceans, what they are, where they are, and why they're worth thinking about, and why the general public ought to care about these areas. And that'll be through the lens of these new observations we've been making in new efforts to model the oceanography of polar regions. And then I'll, time permitting, talk a bit about what we think is going wrong in polar regions in terms of how we model them in climate models, and how our projections for the future in the polar regions have been incorrect, how they continue to be incorrect, and what my group and this larger project I'm involved with is going to do about it. So a bit of background. The polar oceans, or at least I describe the polar oceans as regions that are covered by sea ice at some point during the year. So sea ice is frozen seawater, distinct from glacial ice that you might find in Greenland and Antarctica. And a pretty big fraction of their surface is covered by sea ice at some point, something like 35 million square kilometers. And that's composed in these 2 regions, one in the Arctic and one in the Southern Ocean, the Antarctic sea ice. Together, they comprise an area that's larger than North America and Europe combined. So despite being very far away and very different in terms of their climate system, they cover an immense part of the Earth's surface. And they're very different depending on where you are. The Arctic sea ice is ice that grows inside of a geographic basin, so it's constrained by land. Whereas in the Southern Hemisphere, the Southern Ocean sea ice is growing around a continent and outwards into an ocean and is less constrained. Something we have become aware of within the past 30 years or so is that there's been a rapid change in the conditions of sea ice in the Arctic, driven predominantly by global warming or anthropogenic climate change. The video you're seeing here is a sort of different depiction of how we think about Arctic change. This is sea ice age. So the conditions of the geography of the Arctic means that a lot of the ice that's there used to be multi-year sea ice. That's ice that grows once and then makes it through subsequent summers. That's that bright white material you see disappearing. The rest of the ice is called first year or second year sea ice. That doesn't last very long. It's thinner, it's more fractured, and that's the translucent material. And since I was born, in fact, probably earlier, since the 1970s, we've lost almost all of the multi-year sea ice in the Arctic, and that ice is thicker than first year ice. And so this transition is corresponding with a change in both the thickness and the overall mass or volume of sea ice. We think probably since the 1970s, we've lost half of the ice that was in the Arctic before. For some context, I'm showing you locations that I'll talk about throughout this talk. So there's Umanak Fjord in West Greenland, where we do some on-ice field campaigns with an indigenous community. There's Nares Strait, which is the place where we filmed and experienced this documentary. And then there's the Chukchi Sea, which is an area north of the Bering Strait, where I'll talk about some ecological studies. But like, what is it that we care about when it comes to sea ice? Why does it matter that the ice is going away? So this video you see here was taken in Umanak Fjord in Greenland. That's us on skidoos. You'll see us in a couple more slides from a different angle. And we're crossing from this area that's covered by sea ice in the fjord into an area that's ice-free. So you can see the difference. Ice is brightly reflective, and you can quantify the reflectivity of ice in something called the albedo. So albedo refers to the fraction of incoming sunlight that's reflected from a surface. And when sea ice is present, it can be as high as 95%, especially when you have this snow-covered, bright, flat sea ice like you see on the bottom. In the open ocean, it's only about 6%. That's true just about everywhere. So whether or not sea ice is there can change how much heat is getting into the ocean by a factor of up to 18 times. So it's a remarkable insulator of the polar oceans, and its presence or its disappearance changes the heating of both the oceans, but then the atmosphere and the sea ice itself. So as a bit of a straw man, I'm going to try and describe sea ice for you in what I would call a consensus definition. This is kind of the way that, even if the general public has not heard about sea ice, this is how folks think about it. Many scientists think about sea ice this way. And it comes from these kind of videos I've just shown you in the last few slides. What does it look like? Well, it's this really reflective, solid sheet or surface or blanket. It kind of makes everything boring. It stops the ocean from doing all that much. It blocks the sunlight, and it limits the kind of life that can live under the ice. We all know about polar bears, but one of the enduring features of polar bears is that they seem to live in this desolate, void of an environment. And so where sea ice is a kind of, not all that interesting of a place. Like I said, this is a straw man. I'll burn it down, I hope, in the next 30 minutes or so. But keep this in mind in terms of how folks have tended to think about sea ice over the last several decades. So what is it about sea ice and what is it about polar oceans that makes them so interesting? And what have we learned recently in these areas? And we're going to kind of wend our way through a few sets of studies that illuminate how just really interesting these regions are. One of the first ones that we'll talk about started in 2011. So the image you see on the bottom right is data on particulate organic carbon taken from CTD casts during the IceScape mission, which is in 2011, or research cruise. This is in the Chukchi Sea, that area that's north of Bering Strait. And the colors are particulate organic carbon. They're effectively how much phytoplankton, so these photosynthetic critters that live in the ocean, how much is there. So those numbers are as high as 1,000, and who knows what that actually means. But if you quantify this in terms of how much chlorophyll is there, so how much carbon that's in biomass is in this area, it's probably the highest that has ever been recorded by any ocean-going expedition. So really pretty remarkable. And this is in some area that's close to sea ice, right? Well, what was even more remarkable about this observation was that it took place completely in a region covered by ice. And that ice was a meter thick or more. So that's a bit weird, right? What we saw before and what I showed you in videos and things is that sea ice is this really reflective, bright surface. So, what gives? Why is it that you have not just life underneath the ice, but an absolute proliferation of life underneath the ice, the likes of which you wouldn't see anywhere else? To get there, it's kind of a long story as to why. And so I'll talk through a couple equations here. This will be all you see equation-wise in this talk, and I hope these aren't too daunting. I'm just going to walk through what albedo means and how it's related to the presence or lack thereof of ice. So remember I said that albedo is the sort of reflectivity of a surface. So to get that, you take the solar heating, that's what's called usually shortwave forcing because of the part of the electromagnetic spectrum it represents. That's this purple box. You multiply that by the co-albedo, that's 1 minus the albedo, which in this case would be alpha ice. And that tells you how much sunlight gets through a surface. Pretty simple, right? When you've got an area that has both ice and ocean, say like the entire Arctic, you have to do something a little bit more complicated, though I promise it's nothing more than just a slight algebraic change. You take the incoming heat, you multiply it by the co-albedo of the whole thing, which incorporates both sea ice cover, that's expressed in this fraction C, or the sea ice concentration, and then the ocean cover, which is expressed as this 1 minus C, with its own albedo, alpha ocean. Together, that tells you how much sunlight gets through this mixed surface, which, like I said, could represent the entirety of the Arctic Ocean. And the reason we care about sea ice, remember, is that it has a very high albedo. The albedo of sea ice is probably on average about 0.7 or 0.75, whereas the ocean is 0.06. That's kind of all there is to it. So at the same time, we've seen this decline in sea ice age or sea ice thickness. Maybe more famously, we've seen the decline of sea ice area, so the total coverage of ice. This plot on the left is showing you the average extent of sea ice in each month of the year, taken from what's called a passive microwave satellite measurement. So each one of those pieces of spaghetti is an individual month. And since 1979, when these passive microwave satellites started flying, we've lost sea ice in each month continuously. Since we care about the reflectivity of ice, one thing we like to do is weight the amount of change by the solar cycle. So emphasize changes that happen in summer when the sun is out, and de-emphasize changes that happen in winter when there's polar night and there's no sunlight. So if you do this, you find that the area of sea ice in the Arctic on an annual basis has declined by about 15%. And so going back to our previous equation about albedo, this has given us part of what's called a sea ice albedo feedback on a global scale. So if this is our equation for how much sunlight gets into the Arctic Ocean, well, we know that sea ice area has declined by about 15% since the satellite period began, and that's been compensated with an increase in open water. That means that the increase in open water has represented an increase in solar forcing. And we'll worry about what these units are in another slide. But overall, we've seen across the Arctic Ocean a 6.5 watts per meter squared increase in heating. That's pretty big. When you smear that across the globe, that's a number that's about 0.5 to 0.7 watts per meter squared. And again, I'll show you what that means on the next slide. So, a great question. If you're falling asleep at this point, this is all you need to know. Should I care about the polar oceans? Hopefully you agree with me that the answer is yes. And to illustrate this, I'm going to show you the first figure I think I ever saw as a graduate student, which came from the fourth assessment report to the IPCC. So this came out in 2007, which is about when I started grad school. Wait, 2011. Anyways, so it's quantifying the direct impacts on the heat budget of Earth since the beginning of the industrial period. And so each one of these Y sort of boxes is a different sort of forcing that humans have caused. So greenhouse gases, you can see CO2 at the top, methane, halocarbons, that kind of thing. Changes in land use, changes in aerosols we put in the atmosphere. At the time, the estimate was about 1.5 or 1.6 watts per meter squared. That's the unit used to measure the radiative imbalance, the amount of heating that's happened. And remember that sea ice has contributed about 0.5 in addition to this. So that's comparable, for example, to methane emissions, or at least the estimates about methane emissions at the time. But think about it, right? You know, I said that sea ice and the polar oceans are large, but they only cover 7% of the globe. And if you weight them by the incoming solar radiation, well, the Arctic coverage is only about 2%, actually. And that's declined by 15%. So 15% of 2% is 0.3% of the planet. That's changed from being white to blue, effectively. And the contribution there is more than a quarter, maybe a third of everything that humans have done since the pre-industrial period to pump CO2 and methane into the atmosphere. And that's remarkable. It's this place that we don't experience. That's tens of thousands of miles away from where we live, a total climate system that we don't understand. It's as foreign to us as the surface of the moon. And yet the impact over just such a tiny, tiny region, you might not even notice it, is as big as many of the things we've done to heat the planet. So yeah, these punch above their weight. And I think it's important to care about what's happening in polar regions. But all right, so what about the phytoplankton? Well, we'll get there, I promise. This is another video we took also in Umanak Fjord. Remember, I promised this that we'd come at a different angle. This is 1 day later. So the first one was taken on the 1st of May in 2019. And here's the second one, which is taken on the 2nd of May. You'll see us kind of come into focus. I'm sitting on the dog sled on the left, or I guess it's a kumatik. And you'll see other people we were on the ice with. That's sea ice. That blue stuff that kind of looks like puddly water is actually the same sea ice we saw the day before. That's about 1 meter thick. But you can tell that it's changed its radiative properties. It's the same exact geographic location. And this is because the surface is melted. It got warm, the atmosphere warmed up. You can see there's blue sky. The surface of the sea ice was heated, and this changed its reflective properties. And so, well, this happens. We know this happens. This happened in Umanak, and it happens every single year across the globe. But is this actually something that's important, and is it changing? Sort of the surface properties of the sea ice, are they changing in a way that matters for global climate or phytoplankton? So to talk about that, I'm going to use output from a series of climate model simulations. This is called a large ensemble. What happens is you take a climate model and you start it in 1850 and you move it around a little bit, and then you run 40 simulations of climate from 1850 to 2100. The reason for doing this is that the impact of things like weather, butterfly effect kind of things, can influence the output of your climate model. And by running lots of different simulations, you get an estimate of how much variability things like weather induce in the outcome. So this gives you a good sort of band for what the actual climate variables you experience, how much warming you get, how much sea ice you lose, this kind of stuff. So this is an estimate on the x-axis. This is a phase space diagram. The x-axis is the area of sea ice in summer from one of these large ensemble experiments. And the y-axis is the reflectivity or albedo of sea ice in summer. The black dots come from the pre-industrial period, so before we started heating the planet, and that green is the average. So that's about 0.74. So the average reflectivity of ice is about 74% in the pre-industrial period, and the average ice area is 9.5 million square kilometers in summer. The reason I've drawn that dashed black line on there is to say that, well, absent anything else, it should be the case that as I remove sea ice area, the albedo of the sea ice stays the same. So this is the reflectivity of the ice that's there. Kind of think of it as like a thought experiment. What if I have 2 pieces of ice in front of my face? They both have 74% reflectivity, and then I put one behind my back, and I ask you, what's the reflectivity of the ice that remains? Well, nothing's happened to it. It's this white material, so it should be 0.74. So that's this dashed line. As we remove the area of sea ice, well, it's just sea ice. It's pretty boring. And so you keep the same reflectivity. Obviously, this isn't true. Each one of those red dots is a climate model year from 1850 to 2100. And you can see that as the sea ice area goes down, the reflectivity of the ice that's there is going down too. So something is co-varying with sea ice area loss. That's important and affects the reflectivity of the Arctic, or at least of the sea ice that's there. That's about where we are now. So you'll see how important this change has been in a second, but it doesn't look that big in the overall phase space of Arctic sea ice and Arctic sea ice loss. So why does this happen? Well, the first reason that sea ice thins, thinner sea ice has different radiative properties. We think we've lost about 2 meters of sea ice on average since the pre-industrial period, and we'll lose another one going forward. So this has changed the reflectivity of the surface. The other thing is that this transition, like I showed you in these two different videos, is happening closer to when the sun's out. Normally what happens is you have this bright white reflective snow-covered surface. It melts a bit in August, and that changes it to being darker. And that darkening usually happens, like I said, in August or early September. Now it's happening closer to June, which is peak of the sunlight or peak of the solar cycle. So earlier melting snow changes the reflectivity of the surface, and it's doing it when you have the sun out more. So like I said before, these two images are just taken a day apart. This transition happens very quickly. Now, one thing we tried to understand was how important these two factors in setting the heat budget, let's say, of the Arctic, how important they are relative to each other. So the big thing that folks have cared about, sort of publicly, is the loss of sea ice, its area decline that we talked about before, this 15% number. But we're showing, so if you take the impacts of increased heat going into the Arctic Ocean, the blue bars here are the impact of reducing the sea ice coverage, and the red bars are the impact of changing the sea ice properties itself. And if you integrate these over the entire year, it turns out the biggest increase in solar energy or heating of the Arctic Ocean is not coming because sea ice is declining in area. It's coming because sea ice is changing its properties. The heat is coming through the ice, not around its margins. And so this helps us knock out a couple things from our simplistic definition. Well, sea ice isn't actually all that reflective. When the surface melts, it can get pretty see-through. And it doesn't necessarily block sunlight. That's because the ice is becoming thinner and it's revealing that a lot of heat or solar radiation is getting directly through the ice. And this is sort of a lesson that focusing on the retreat of sea ice, for example, the decline of September sea ice cover, might be obscuring dramatic changes that are ongoing near the peak of the solar cycle. I promised I'd explain the blooms, and this is what it is. Changes to the sea ice itself are allowing more sunlight to reach through the ice and seeding these massive phytoplankton blooms. This video is showing you areas of the Arctic Ocean from the 80s to present in which you have the conditions required to permit widespread blooming. As little as 20 years ago, it was unlikely that these things existed. In fact, they were rarely observed, if ever. Now, they're probably happening across maybe 50% or more of the Arctic Ocean, which remains covered by sea ice, which, remember, is supposed to be really reflective and not allow life to exist underneath it. So primary production in the Arctic is shifting underneath the ice in a way that wasn't possible before the period of anthropogenic change. Something that might be of interest to you is that we actually found, and we've just published a paper showing this happening in the Southern Ocean too. We recorded dozens of these events, big blooms, happening underneath a different type of sea ice that hasn't changed much over the global warming period in the Southern Ocean. You don't necessarily just have to take my personal word for it. We've observed co-synchronous increases in this thing called atmospheric iodine. That's a byproduct of photosynthesis that happens in sea ice or under sea ice. And if you look at this plot on the left, that's the shaded blue thing. So over the past 40 years, iodine levels have increased by a factor of 3 in cores recorded in Greenland. And all the other factors that could give rise to increased iodine, say human production or changes to ozone, have not increased in the same way. But if we look at ecological changes, that's this red line, which quantifies the amount of blooming underneath the Arctic sea ice, that has increased basically by the same factor and strongly co-varies with the increase in iodine. So the conclusion that we came to was that ecological change is driving atmospheric chemistry changes as well across the Arctic Ocean. So summarizing this, well, we kind of have to kill the limiting life thing. There's widespread productivity, widespread phytoplankton living underneath the sea ice. And this has been triggered, or our understanding of this phenomenon has been triggered by changes to the sea ice over the global warming period. But still, we've got that sea ice is this solid sheet that stops the ocean from doing anything fun. And that's where we'll talk a little bit about enduring ice, or beneath the polar sun, or Albedo, a few names for this movie, depending on what country you're in, which was an expedition we undertook in 2017 and 2018 in Nares Strait, that region north of, or on the sort of on the border between the Arctic Ocean and northern Canada and Nunavut. And the concept here was that we were going to make a film about some young scientist, I guess that's me, doing the kind of work that he likes to do and exploring this place that's called the Last Ice Area. So the reason it's called that by, I think, the WMO is that it's predicted to be the place where sea ice is still really thick and composed of these big multi-year sea ice floes and will remain the longest. So we were going to have this film about a sort of older explorer and the younger scientists going off and getting wistful about how things are changing in the Arctic and how nothing will be like it once was, or something like that. It's a lot worse than that, I promise. This is a video of what, this is going to show you why we thought we could do what we said we would do, which was kayak in this strait. The reason is this last ice area, theoretically, was full of these big pieces of ice. So the top part of this is the Lincoln Sea. That's an area of the Arctic. You can sort of see Ellesmere Island on the left. That's Canada, and Greenland on the right. And that opening is the strait. So this ice is really thick. It jams up the strait, and the ice predominantly flows north to south. Currents are flowing that way here. And so it stops ice from being exported from the Arctic. And in the summer, it's warm enough that ice isn't freezing. And so you can actually kayak in this area. And that's actually something that's been done, not just by us, but by Inuit for hundreds of years and longer. So this is something that's been known to be possible in the recent past. This is a satellite image of what happened in 2017. There's that jam, and we've hit about May, and that's what happened to us. So rather than this big jam forming and opening up a clear strait, sea ice flowed directly through Nares Strait. So what we found was none of this multi-year thick sea ice at all. All of it was this first-year sea ice that was about 3 feet, 4 feet thick, and it was moving fast, really fast, 10 miles an hour plus, and it weighs about 1,000 kilograms per meter cubed. Pretty terrifying. None of the ice we found during this period in both years was this multi-year-old sea ice that was suggested to be there. And this is a problem, and we're jumping ahead a little bit here, that our estimates of what sea ice exists there in Nares Strait, you can kind of see it, I hope you can see my cursor over here, is that this region is supposed to have 3-meter thick ice. At least that's what everyone thinks. More on the climate models later. So the movie that was supposed to be some wistful look back at, tales of times gone by, became much more about survival. And so that's us in the boats. This is on a beautiful day. You'll see what it actually looked like on most days. We had to navigate what was a massively flowing strait covered by huge pieces of ice, huge relative to us, but not very huge relative to the Arctic. And so sometimes this involved this kind of brilliant little lily padding, but more often it involved portaging, meaning pulling 1,000-pound kayaks on our backs. You'll see in just 1 second what that looked like on almost every single day. That's us yanking a massive piece of equipment over essentially rocks. It was a tough time. And it taught us an important lesson, that sea ice of this sort of old multi-year character does not appear to remain in the places it's supposed to remain for 50 years or more. This is particularly important not just for idiot explorers like us, but also to people who depend on the presence of sea ice or have historically depended on the presence of sea ice. So indigenous communities in the Canadian and Greenlandic Arctic. And these folks depend on the sea ice or its platform in fjords for infrastructure, so getting between communities, for fishing from, for hunting, and of course for tourism. And so one thing we've been working on in Umanak Fjord, you'll see the little location pop up there in West Greenland, is working with the local community on trying to understand how Breakup has changed their way of life and how it will change going into the future. And a preliminary or first result that we obtained while in West Greenland was a look at how the response of ice in coastal communities depends on the location of those communities. And what we found was that the areas that are the coldest, so the ones that are usually used to thick, substantial sea ice covers, are also experiencing the most rapid change. So the places that are less equipped to deal with rapid sea ice change, namely those in northern Canada, so like northern Baffin Bay, are finding that the sea ices, or the duration of the period where the ice that they use for transport is viable, is declining by 7 or 14 days over the last decade. So fairly dramatic change. And so it's obvious now that sea ice actually isn't this big solid sheet of material. It's really mobile, and that mobility is changing with a changing Arctic or warming Arctic. And this is impacting, again, folks who are trying to film wistful movies, but also human beings that live in the Arctic, and changing the way that they have to interact with the natural environment. So we sort of gotten this from before, but the thing about sea ice is it's not at all like this sheet. It's actually a composite material of individual pieces, and those pieces are called floes. So you can see these floes at every scale you look at the ice cover. The bottom left is an icebreaker that's about 100 meters long, and it's surrounded by 10-meter floes in the Southern Ocean. But on the right, this is a wide satellite image of the Bering Strait, so between Russia and Alaska, and there are pieces of ice that are 10 or more kilometers wide. And these floes control how sea ice evolves. Here's an example of how this works in looking at the ocean. Remember this image from before? This is looking at the sea ice edge. Well, when sea ice is present, so this is showing on the right, this diagram, the shortwave forcing. So the solar forcing, which is expressed in units of watts per meter squared, and it can be as high as 320 watts per meter squared in the summertime Arctic. About none of that gets to the ice, but almost all of it gets through the open water. And this leads to changes in the surface properties of the ocean underneath the ice or at the ice edge. And that does something to the ocean. Exactly what? Well, we're not totally sure. But I'll show you an example of how this operates. Here, using these high-resolution simulations, so the top is an ice edge, the bottom is open water, and all we're doing is heating this from above. And what happens is this gradient leads to the establishment of geostrophic jets, which are unstable to what's called baroclinic instability, or submesoscale baroclinic instability, which drives melting at the boundaries. So the melting of the sea ice proceeds from the edge upwards. And we can look at how this expresses itself in more realistic configurations. So you'll see two simulations, one with lots of small pieces of ice, another with one big piece of ice, and these eddies that sort of emerge at the boundaries, and they quickly wipe out the small floes on the left. But when you have this one large floe, which started with the exact same area and volume, it takes a really long time to bring the heat from the open water region underneath the ice. And this means that changes in the sea ice geometry really strongly impact how long it takes the sea ice to melt. In these kind of simulations, it can take 3 or 4 months to go from what you would expect with small pieces of ice to one large floe. It can take as much as 120 days difference to melt out the ice for the same starting conditions and heating. At the same time, we know it's not just the ocean circulation that's affected or influences the ice, but also that waves propagate long distances into the sea ice and change its geometry. And one of the tools we use to understand this is altimetry, or the IceSat-2 altimeter more recently, which is essentially a laser in space that circumnavigates the globe 14 times a day. And it takes insanely high resolution pictures, or not pictures, but measurements from the surface that tell you how high it is. Pretty remarkable what you can do with just that information. So this is an example of one of these returns from IceSat-2. You'll see it again on the next slide. This is over sea ice, and it's showing the height above the ocean. So a couple centimeters, 20 to 40 centimeters or so. Some big ridges and peaks up to a meter. This was taken on the 22nd of March in 2019. You can see on the top left, this is the colors here are the significant wave height. So how much wave, essentially how much wave energy there is. This is associated with a big storm that passed through the Barents Sea. It's the area north of Norway. And it passed through on the 22nd. The 23rd, we had another flight or overflight by IceSat-2. That's that green line, if you can see it. And you'll see a remarkable change in the properties of the return. what you see coming back from this altimeter, the height of the surface, again, this is 100% covered by sea ice, is waves. These waves are, in this case, 100 kilometers in, but we track them going as far as 2,000 kilometers into the sea ice. So waves are propagating long distances, bending the ice, fracturing it, causing ocean mixing, all sorts of stuff. And what we've been working on for quite a while now, or at least a couple of years, is understanding the degree to which waves are actually responsible for driving sea ice change across both hemispheres. So what fraction of the ice cover do you have this strong ocean ice interaction? So here are examples of maps in the southern hemisphere, looking at regions colored in red, where waves are found in the ice year round, throughout a given month. You can see basically it rings the perimeter of the southern hemisphere, and this is also true in the Arctic. We can use these measurements of waves and quantify just what fraction of both hemispheres is influenced by waves. And that's shown on the right. So this is from 3 years of data. The x-axis is a given month. The red is in the southern hemisphere, and the y-axis is the fraction of the ice cover that's influenced by waves. For red, again, the southern hemisphere, blue, the Arctic. And so it peaks at like 50% of southern hemisphere sea ice. That can be as much as 6.5 million square kilometers is inundated or continuously under the influence of ocean waves. So quite a bit different from this sort of weird wide area that isn't really moving very much. It flows and it experiences and modulates the presence of waves. So that kind of kills off our big consensus definition. It doesn't really suppress the ocean. In fact, it's strongly coupled to the ocean. It's not really blocking much sunlight. Life seems to love it under the ice. It's not all that reflective, and it's not very solid at all. It's this composite material that's tightly coupled to interactions both with the ocean, but with waves, with ecology, and with itself. So I guess in the next few minutes, let's see, 10 minutes, let's say, I think, I'll talk a little bit about climate modeling and just give you a flavor for why my group and this project I'm involved in called SASIP is interested in improving climate models in polar regions. So I'll try to give you an idea of what it is that matters for climate modeling. And for sea ice, because we know it has this weird geometry, there's two scales that are important for us to consider. The first one is what's called the deformation radius, or the Rossby radius of deformation. This tells you how large the changes in surface forcing or gradients in the ocean have to be to result in these kind of eddy things we were looking at before. So the Rossby radius of deformation just tells you at what length scale you expect to have ocean variability important, or take up gradients in the surface forcing, changes in the surface forcing. The second one is the grid scale of your climate model. So if we're concerned about sea ice and sea ice flows, well, if those flows are larger than the grid scale, we're good because the model theoretically should be able to resolve them. The deformation radius in the Arctic is on the scale of a kilometer or so, maybe 10 at most. And the grid scale of climate models is usually around 10 kilometers at best, typically about 40 or 50. So you can kind of see where this is going. But still, we have to know how big are the pieces of sea ice that dominate sort of the discussion in the Arctic. And to do this, we've turned to, again, altimetry, but different sources of altimetry. NVSat, Cryosat-2, which is a radar altimeter, a totally different thing. And ISAT-2 again. ISAT-2 gets the heart emoji because it is much higher resolution, much more precise. And what we do is we take these images. So here's an example of Cryosat-2 returns overneath sea ice. And all you do is you count up when they have ice and when they have open water. And you use that in some complicated math to obtain two-dimensional statistics like the fraction covered by ice, or the flow size distribution, the representative sizes of piece of ice, etc. And we'll skip over all that technicality and just talk about how big flows are. So the bottom left and bottom middle are looking at the average flow size in the Arctic in a given month and average over the entire year. And the number you need to see here is about 5. About 5 kilometers is the representative size of pieces of ice in the Arctic. And there's a plot sort of averaged over the entire 8-year period that Cryosat was operational at the time. So showing you that they're biggest closer to Canada, Greenland, but smaller outside. This is kind of a problem. See, because the Floe-Scale, there's our beautiful little floe. This one's like 2 kilometers across, I think. And it's much bigger than the scale necessary to cause these kind of ocean eddies to emerge, like we saw in those previous videos. So it's big enough to cause these ocean changes that we know can result in differences in, sort of ocean variability, sea ice loss, that kind of thing. But it is way smaller than the grid scale of a climate model, which tends to be 10 or more. So it's kind of the perfect storm. You have this thing that you know has an effect that you have no chance of evolving. It's just too small. Actually, it gets worse. The sea ice models in use in climate models don't actually account for this effect in any way. They treat sea ice like our consensus definition. It's a sheet that sort of ebbs and flows. It doesn't have all that much interesting geometry to it. So this is all well and good, but I suppose we need to convince ourselves that sea ice models need to actually be improved. And there's a few examples going back to at least the 80s where folks were pointing out issues in the way climate models were evolving sea ice. One of the most famous papers was this one in 2007. This is looking at, on the x-axis, September sea ice extent, and the y-axis, September sea ice area. And the red is the observation, and each one of those spaghetti plots is a different model. And what Julian Struve and others pointed out at the time was that sea ice was declining much faster than any model would predict. It seemed like we did better with the next generation of climate models, but it was revealed not long after that the reason for this was that many of those climate models were overheating. I won't go too much into detail here, but just say that the models that represented the sea ice loss were the ones that were maybe twice as warm as the ones that didn't. So it was the same problem as before, except now some of our climate models were warming too much. And I'll skip this part just in the interest of time. But just say this big, bright statement. One of the things we've worked on in my research group is understanding whether sea ice models and their representation in global climate models have improved over the past 30 years, and whether biases in these models is explainable by some uncertainties inherent to climate. And the answer is no. And we've known this exactly in the same way, dating back to at least the 80s. So what gives? Why is this happening? Well, it goes back to our diagram that we were talking about before. In a sea ice model or in a climate model, you have what's called a sea ice concentration. It's the fraction of a region that's covered by ice. And so you can have situations like the one we showed at the ice edge, where you've got a lot of heat going through the open water and almost none going into the sea ice. But in a climate model, you only have one ocean temperature. And that ocean temperature has to be forced by something. So rather than the 0 from the sea ice or the 300 from the open water, you take the average, which is 150. And that's way too little for the ice covered, way too much for the ice covered regions. It's going to cause more sea ice melting. And it's way too little for the open water. It's wrong in both cases. And it implies something weird happening below the model grid scale, some mixing that's happening. We can quantify this, and we call it the eddy exchange flux. And it's this function of concentration. It's a quadratic function of sea ice concentration. We've tried to quantify this in a number of different ways, and we call this something like the polar tempest. It's this weird thing that depends only on, well, it doesn't depend on anything to do with sea ice or the ocean. It's this thing that happens below the grid scale of a climate model, and it's huge. If you took all the sunlight hitting the Arctic Ocean, a third of it is instantly whipped around below the climate model grid scale because of this implied geometric flux. And if you quantify the amount of freshwater forcing, so precipitation, that has to be moved instantly underneath sea ice edges, it's on the order of 1 or 2 sphere drops. So a sphere drop is 10 to the 6 meters cubed per second. This would make the polar tempest probably the largest current in the Arctic Ocean. So we think climate models are doing a bad job in polar regions because they're not matching observations and they have these implicit biases in the way they represent the ocean. And so we've been funded for the next 6 years as a part of the Scale Aware Sea Ice project by the Schmidt Futures Foundation, so it's myself and a pretty distributed team now, to build a new climate model that represents sea ice in the polar oceans. And this is taking two main advances, one that I'm responsible for and won't talk about, which is the subgrid scale closure, so how you understand sea ice geometry when you can't resolve it. And another one that makes much better movies, which is the grid scale rheology. So how does sea ice look on large scales, and how do we model that better as well? The reason for this large scale modeling is differences in climate models from observations like the ones you see here. The bottom left is a video of a real sea ice model that's in operation that's used to produce data for the IPCC or the coupled model in our comparison projects. The right is observations of sea ice cracking. So that's a real sea ice. They're integrated over the exact same period of time. And you can see that sea ice sustains these really large cracks. They're called linear kinematic features or leads or something like that. And they don't exist in a climate model that uses a certain set of equations that simulate sea ice as this sort of plastic sheet. So they're clearly missing. And the big advance that's been made by our project is the introduction of new sea ice equations or new sea ice physics that allows for the propagation and generation of these big cracks. It sounds pretty simple, but it's taken about 10 years. And what you can see happen is by virtue of being able to retain these large cracks and features like this, you get sea ice that looks like what we saw in Nares Strait, this kind of flow or plate-like material that flows in weird ways that can move through straits. That's basically sea ice. And we can just compare them next to each other. So these are the sea ice model we've been working on in the middle and the sea ice model that's standard on the top right. And you have these two very distinct regions, which we've been working on quite intently, the large scale fracture patterns, linear kinematic features and leads, and the very small scale. So the flows that are influenced by ocean surface wave, which are a bit zoomed in on the bottom right. And both of these combine to create a truly scale aware or scale variable model for sea ice that helps us make better predictions about the future. Though it's a good question to have is this actually going to improve our skill? And that's why we're working on this for the next 5 years. And hopefully the answer is yes. So just to wrap up, polar climate systems are cool. I think they're fun to study, they're important, they have an outsized influence, and they're very unique. And that's because of the presence of sea ice and its coupling to the ocean. And our group, both at Brown, in Auckland, and across the world, is working to improve these climate modeling, our climate modeling capacity and understanding of these areas. So thank you very much.
Thanks, Chris. Can you hear me okay?
I can.
Great. So there was a round of applause that you probably didn't hear. I'm going to turn the floor over to questions from students. Does anyone have a question? Is that a hand way over there? No. Over here.
Okay, wait, is this? Yeah, okay. So, you mentioned, that there was Antarctic ice that,
Yeah.
like, that had a bloom underneath it, but hadn't changed much since from, like, the Industrial Revolution or whatever. Why was that able to have a bloom if it, like, hadn't thinned a lot? Or, like, gotten more transparent?
That's an excellent question. So one of the main thing that these critters need to bloom or to grow is light. So the problem when you have sea ice is that it's reflective, for one, and that you have polar night. So you don't really get very much sunlight throughout for an entire 8 months of the year. It was just kind of assumed that the properties of sea ice were such that you couldn't get light through it. But what we know about the Southern Ocean is that different to the Arctic, you have these little pancakes in a lot of the places. So rather than these big chunks of ice that might be several kilometers across that really can block the light when they're there and their surface is snow covered, you've got all these little regions around the sides of the ice in the Southern Ocean. And it's actually not a very big fraction. It's like 5%. So what we found was that even when you had just 3 or 4 or 5% of an area that allowed light to get through it, you get these blooms basically every time you have the right nutrient conditions. And we just kind of assumed this wasn't happening. If you go into a climate model, oftentimes the sea ice concentration will be exactly 100%. And this small difference, which really is not, it's hard to even notice if you looked at an image of it, is enough to allow these phytoplankton to grow and bloom.
No? No? Yeah.
So if the sea ice in the Arctic is thinning such that you have more blooms underneath, so you have an increase in primary productivity, what's happening for the rest of the food web?
Yeah, that's an excellent question. We don't know. Remember that the first sort of observation of this effect was in 2011. Well, to be fair, it actually was in like the 1950s. So the US Navy wrote up about a phytoplankton bloom they observed a long, long time ago, but it was not digitized and it was very difficult to find. So, but it hasn't been a topic of study, and the changes happened over most of our lifetimes, right? So it's hard to exactly know. I think there's a strong effort across the US, at least, and Europe as well, to understand changes to the entire ecosystem structure. Like, are these blooms supplementary, or are they replacing what normally happens in the Arctic, which is when the sea ice goes away, you get another type of bloom. And we know that the sort of megafauna and stuff track those. That's because, the fish track them and narwhal track them and things like that. So as far as I understand it, the structure of the food web is aware of the presence of blooms and tracks them, but we don't really know what's going on with these under ice blooms. And we think they occupy, huge swaths of the Arctic. We just don't know if there's the nutrients are getting back out to see the second bloom or not. But it's definitely an area of active research.
Other questions?
Thanks for a great talk. I'm just curious about the influence of some of your findings on our understanding of polar tipping points, and whether or not some of your models will be reflected in the next IPCC report. Thanks.
Sure. Yeah, so I don't know that we have focused very much on rapid change, so tipping point style stuff. Though I do have a graduate student who's working on trying to figure out if changes to sea ice surface properties remove the potential for rapid tipping points in Arctic systems. But we've certainly promised that in the next IPCC go-around, we'll be producing results. But most of the progress that's taken place over the last 10 years has been preparing this model to exist as a standalone sea ice framework. And so a huge push that is ongoing right now is to get this coupled into have an atmosphere and land surface and ocean and all that stuff that are at the IPCC stage. So I would love it, and I think we would all love it, and we hope to be doing IPCC class runs and compare. That's our whole entire focus, is compare our results to others. Whether we can pull it off is a big question. Most of these climate model groups have huge teams and huge amounts of resources, and it's a really difficult problem to get 150, 250 year simulations. So we've gotten 3 years, which we feel pretty good about, but that means we've got a long ways to go.
Anybody else? I have a quick question. Is there anything to be gained in resolving flows by changing the grid shape in the poles?
Yeah, so unfortunately this could happen in the model that we've built. So if you refine the grid, make it smaller, you do actually, like you could maybe have seen in one of those videos, you can actually get real pieces of ice. But that won't happen even in the highest resolution model that is using a standard sea ice physical system. So I'll see if I can't find it. Because when I was talking about this, so this is the model you see here. It's called the MIT GCM 4320 Latlon cap. So who cares what any of that means? But the resolution here is 750 meters. So this is by far the highest resolution experiment that's ever been run, made probably in the Arctic. Really, really high res. And there's no flows there. Like you would see them if they were there in some of these physical fields. So you can't resolve pieces of sea ice using the system of equations that's currently used in a climate model. In fact, they were designed explicitly when they were written down in the 1950s to represent pieces of ice that were 5 to 50 kilometers in size, that were 10 times smaller than the domain you were simulating them in. So grid spacings of a degree, a few hundred kilometers. And now people are trying to use them for 10 kilometers where the pieces of ice are larger than that. So yeah, it's just not, it just won't happen given the current generation of sea ice model. And that's kind of one of the reasons we are optimistic about our approach.
Let's give Chris one more round of applause. Thank you so much for joining us today.
Thank you.
You are free.
Sweet.